Welcome to this video on NQR spectroscopy applications. Let's explore the quadrupole interaction and splitting of energy levels. Nuclei with a spin I greater than 1/2, combined with a non-cubic electron or ligand distribution, generates of different nuclear energy levels with nuclear magnetic quantum number Mi values are +I to -I. The number of NQR transitions possible depends on whether the system is axially or non-axially symmetric, defined by the asymmetry parameter eta. The number of transitions varies significantly based on the spin I and whether ETA is 0 or non-zero. For half-integral spins I equals 3/2, 5/2, 7/2, I-1/2 NQR transition are possible, and for integral spins with eta equals 0, I NQR transition are possible, and for integral spins with eta does not equal 0, 3 I NQR transition are possible. The electric field gradient, EFG, is influenced by valence electrons and lattice symmetry. For symmetric electronic configurations, there is no valence electron contribution. Lattice symmetry determines the lattice component of the EFG. For a particular NQR nucleus, chemically non-equivalent centers, experiencing different EFG, will give different NQR signals widely spaced. For chemically equivalent NQR nuclei, occupying non-equivalent lattice sites, i.e., Q valence electron same but Q lattice different, will give different NQR signals but closely spaced. This also leads to split the signal, producing a multiplet-like signal. NQR spectroscopy can study phase changes in crystalline solids. As seen in K2BR6, the NQR spectrum changes with temperature, indicating that as temperature is lowered, the crystal symmetry gradually drops, leading to more NQR lines. NQR can identify the nature of bonding and estimate ionic character. The nuclear quadrupolar coupling constant, EQQ, depends on the effective electronic configuration. Specifically, valence electrons in p orbitals are the most important factor for EFG, while s orbitals do not contribute. D and f orbitals contribute less to EFG, but d orbitals may produce some asymmetry. Increased ionic character in a bond leads to a more symmetric electronic configuration, causing the EFG and EQQ to decrease. NQR can identify chemically inequivalent and crystallographically inequivalent NQR active sites. For example, silicon tetrachloride shows 4 signals due to crystallographically inequivalent Cl atoms, despite being chemically equivalent. For K2TCl6, 1 peak with no splitting is observed, due to chemically equivalent halogens, hence octahedral symmetry preserved in solid state. In PHASCl4, the axial and equatorial Cl atoms are chemically inequivalent, producing 2 peaks. Each peak is further split into a doublet due to the Cl atoms occupying different non-equivalent lattice positions. Axial Cl atoms withdraw more electrons from AsCl, as axial Cl is close to Cl-anion. EFG approximately equals 0, i.e., more ionic. Hence, EFG of axial Cl is lesser than EFG of equatorial Cl. Hence, NQR peak for axial Cl is seen at lower frequency. Phosphorus pentachloride provides a complex case, crystallizing as phosphorus tetrachloride plus cation phosphorus hexachloride -anion. The phosphorus tetrachloride plus cation gives 4 lines, and the phosphorus hexachloride anion gives 6 lines, resulting in 10 peaks due to crystallographic non-equivalence. For PFCl4, 2 expected peaks with a 1:3 ratio are observed. 1 peak for axial 2 Cl atoms, and 1 peak for equatorial 3 Cl atoms. No peak splitting as axial and equatorial Cl atoms occupy crystallographic equivalent lattice positions. However, in K2Ti6, the expected single peak splits into a triplet due to halogens occupying 3 different types of lattice points. For bromine monocyanide, the 14 NQR spectrum shows 2 peaks, a doublet, attributed to a non-zero asymmetry parameter. X-ray studies show the N centers are crystallographic equivalent. Hence, doublet signal is due to ETA does not equal 0. Out of 3, 1 is weakest and ignored. Hence, doublet arises from the asymmetry parameter. In solid state, interaction among different chains leads non-axial symmetry. The 7981 bridge NQR spectrum shows 1 peak at a higher frequency due to the formal positive charge on bridge. MX3 compounds exist as a dimer with bridging and terminal halogens. The NQR spectrum shows a doublet and a singlet. In dimer, bridging X is more anionic, and feels less EFG and appears at lower frequency. Also, they are chemically and crystallographically equivalent, hence singlet. Terminal halogens are chemically and crystallographically non-equivalent, hence doublet. TeCl4 crystal is constituted by TeCl3+ and Cl- ions. The expected 2 lines become 6 NQR lines in the actual spectrum due to crystallographically non-equivalent TeCl3+ pairs. The Cl ions are NQR inactive due to symmetric electronic configuration.